Now let us see what a probability distribution is. We are dealing with a large amount of data, and working with large amount of data is always very difficult. So if we know how this data is, or how this data is distributed, then it becomes easier for us to represent the data with very few number of parameters, and this is where this probability distribution idea comes into picture. The probability distribution describes the likelihood of different outcomes in a random experiment or statistical analysis. So what all the possible outcomes are there for a random experiment or a statistical system, and then knowing what is likelihood of that particular outcome. So if we know the likelihood of each outcome possible for any random experiment, then we can plot this, and what the plot we get is called probability distribution. The probability distribution provides a mathematical representation of the possible values of a random variable that can take, and the probability associated with each value. So that means mathematically we are representing what all possible outcomes of any random variable are, and for each outcome what is the probability of occurrence. So this is what probability distribution is, and this is basically represented in a mathematical form, and once the big data is put into one mathematical expression, then for any given input we can get the output. That's a basic idea of finding this distribution. So basically there are two types of distributions depending on the type of the outcome of the experiment. If the outcome is discrete in nature, then we have discrete probability distributions, and if the outcome is continuous in nature, then what we have is continuous probability distribution. So let's see various types of probability distributions which are considered as standards and which cover most of our statistical problems. So let's begin with a discrete possible outcome. So one is a Bernoulli's distribution. Here the Bernoulli distribution describes a single binary outcome like a success or failure or yes or no, with a fixed probability of success P and failure, that is Q, which is equal to 1 minus P, because total probability of any binary outcome is 1. So probability of success is P and probability of failure Q, then P plus Q should be equal to 100%. So here the examples include flipping the coin or any experiment which has got a yes or no as outcome. Next we have is a binomial distribution. This represents the number of successes k in a fixed number of independent Bernoulli trials. Bernoulli distribution talks about the probability of getting a success in the experiment, and if we continue repeating these experiments whose outcome is a binary, then what is the probability that successively k number of success are obtained from independent Bernoulli trials? Here the parameters include number of trials, that is n, and the probability of success, that is P. So it's totally, there are n number of Bernoulli experiments conducted, and we know that the success rate of any Bernoulli experiment is P. Then, so out of n experiments, what is the probability that continuously k times we get success, or yes, yes, yes as answer, or in simple, we are talking about flipping a coin. Then if we continue flipping the coin one after other, then what is the probability that continuously k number of times we get a head if we have conducted this experiment n number of times? So that's something to do with the binomial distribution. The next one is a Poisson distribution. Here, this models the number of events occurring in a fixed interval time or space. It is often used for rare events with a known average rate of lambda. What is it saying? It's a model that models the number of events occurring in a fixed interval of time or space. So what it says is in a given time. So if we consider any queuing system, then in given amount of time, how many number of people get added to the queue. So that is a number of people getting added to the queue in a given number of time is, if you are talking of this type of problem, then we call it a Poisson distribution. Now coming to the other side, there is continuous distribution. One is a very commonly used, that is a uniform distribution. That is, in a given range, all values are equally possible. So here the probability density function is a constant within a given range. Most important thing is the normal distribution, also called Gaussian distribution. It's a symmetric bell-shaped curve with a mean mu and a standard deviation of sigma. It is widely used due to the central limit theorem and is often encountered in almost all natural phenomena. We'll see in detail where they are useful with some examples. The next one is about exponential distribution. This one models the time until an event occurs in a Poisson process. So the Poisson was talking about in a given interval how many times a particular event occurs. That means, like it says that in a given time how many people get added to the queue. Maybe an example. Or if you are on the road, you can just keep watching that in a given time how many vehicles pass before you on the street and so on. So that's a Poisson, but the exponential is the other way of talking of it. So it is talking about how much time it takes for the next event to occur. So if you are talking about someone adding to the queue, then once you start counting the time, then it is talking about the probability, how much time it takes for the next person to get added to the queue. Or if you are watching the road, then one car has passed, then how much time it takes for the next car to pass before you. So this is what is the exponential distribution. Then we have gamma distribution that generalizes the exponential distribution to account for waiting times until k events to occur. So here in the exponential distribution, we said so much time it takes for the next person to add to the queue. Here it talks about how much time it takes for k number of people to get added to the queue, or how much time it takes for the next k cars to pass before you on the street and all that. Then we have chi-square distribution. That's a special case of gamma distribution, and this arises in hypothesis testing, particularly in the context of comparing observed and expected frequencies. So when we are talking about frequencies, so we one side we have actual observation, and another side we had expected something as an outcome. So when you want to compare these two, we're using hypothesis testing, whether what we expected is it being observed or not. So if you are trying to do such an hypothesis testing, then chi-square distribution comes to our aid. Then we have beta distribution, and this describes the distribution of a random variable constrained to the interval 0 and 1. It is often used as a prior distribution in Bayesian statistics. Then we have logistic distribution. It's a S-shaped distribution that resembles the normal distribution. It is commonly used in logistic regressions and modeling growth processes. So the main advantage of logistic distribution is that whatever be the range of input, it can be extending from minus infinity to plus infinity, but the output will be limited between 0 and 1 only. So that's a S-shaped distribution we have, and it converts an infinite range to uh, 0, a range between 0 and 1 always. Then we have Cauchy distribution, a symmetric distribution with heavy tails. It lacks defined mean or variance and is used in various applications including physics, finance, and so on. So these are the various pictorial representations. So the normal distribution, as we discussed, it's a bell shaped. The central peak value is what is called the mean, and the width of this is something to do with the standard deviation or the variance. Then we have horizontal line, that is between two intervals it is uniformly distributed. Then Cauchy distribution is almost like normal distribution, but its structure or the shape is little pinched. And T distribution also looks like a normal distribution with little deviation. Then F distribution, chi-square distribution, exponential, and so on. So many different possible distributions are shown here. A power normal distribution, beta distribution, and so on. So there are many such distributions are defined in the statistical world that will help us in converting a big data into few number of parameters. For example, if we know that our data is normally distributed, then we can just represent the whole millions of data by just two numbers, one where the mean is and how much is the variance. Just two numbers are sufficient to represent the big data. Same way for every distribution, one or two or few parameters are sufficient to describe the whole set of data. So that's a parametric way of representation of the data. So the probability distribution helps us in understanding how the data is distributed, and it helps us in comparing whether the two set of data are similar or dissimilar just by looking at the distributions, looking at their parameters, comparing them. We can just easily tell whether the two distributions or whether the two data sets are similar or from the same process or not. And many such things come to our aid when we work with probability distribution. So these will simplify much of our work when we are dealing with big data, data science, and data analytics. So as of now, that's it for probability distribution. Many more issues to discuss in the coming sessions. So keep watching. Thank you.